Okay, hello, welcome back to General Chemistry 1 lecture. Today I'll be going over Quiz 9, Stoichiometry. I will be reviewing the answers to the quiz. Stoichiometry is another key important skill that you need to have. Not only is it important for the remainder of this course, but it's important in chemistry, general chemistry too, and it will follow you in any higher level chemistry course that you wish to take. So it's important that you have a really good understanding of stoichiometry. That being said, let's get started. So number 1 asks us what's conserved in the reaction below. So nitrogen gas is combined with fluorine gas to give us nitrogen trifluoride. So I do want to point out here that, before I get started, you'll see that I have added some extra space in between questions just to allow my messy handwriting to have some extra room. So that you wouldn't have noticed on your quiz, but just for the sake of this writing and this video, I added some extra space. But for number 1, one thing I want to point out is that on our reactant side, we have 4 moles. And on our product side, we have 2 moles. So we're actually losing moles here. So moles is not conserved. So when we talk about the law of mass conservation, which was something in your lecture material for this week, that does not cover moles. That covers mass. Moles are not necessarily mass. So in this reaction, moles are not conserved. Mass, however, will always be conserved. So we can eliminate answer A, answer D, but it could be answer B, C, or D. So let's take a look. So we actually are conserving mass. So mass is being conserved. Are we conserving atoms? Well, yes. We are conserving atoms because if you look at the equation, we always are going to conserve atoms in a chemical equation. But are we conserving moles and molecules? No. So the answer here would be C, only mass and atoms. I do have another lecture note material on this question. I just don't want to spend too much time on it in this video. So if you are still confused about this question, please refer to that note material in the lecture packet. Number 2, now getting started with the stoichiometry, asks us how many moles of nitrogen gas are needed to react with 0.5 moles of lithium. So let's make sure our equation is balanced, and it is, so always make sure your equation is balanced. So we're given 0.5 moles of lithium. It's lithium metal, it's a solid. And we know that we need to establish a mole ratio here to get the moles of nitrogen gas. And per the balanced chemical equation, for every 6 moles of lithium, I'm going to need 1 mole of nitrogen gas. And that's all we need here because we're asked for moles of nitrogen gas. So when you do 0.5 divided by 6, you'll get a number that should be approximately 0.833 repeating moles of nitrogen gas. So the answer here would be E. Number 3 says that calcium carbide reacts with water to produce acetylene. This is a common reaction you would see. It's actually the reaction that was used in mines to produce light in little canisters. I would probably do a demonstration of this if we were in person, but it's a cool demonstration. But anyway, calcium carbide reacts with water to produce acetylene gas. Production of 13 grams of acetylene gas requires consumption of how many grams of water? So here this is one extra step than the last problem because we're asked to go from grams to grams. So we have 13 grams of acetylene. We know that 1 mole of acetylene is 26 grams because carbon is 12. 12 times 2 is 24 plus 2 is for hydrogen is 26. Per the balanced chemical equation, we know that for 1 mole of acetylene, we need 2 moles of water. And now we need the grams of water. And you might as well just memorize the mass of water because you'll be using it all the time. And the mass of water is 18 grams. So you can always cancel your units. It's a good practice to make sure that all your units look good and we're left with grams. And when you do this on your calculator, you should get approximately 18 grams of water. And that's just pure coincidence with the 18 there. So the answer here would be C. Number 4 says that lead 2 carbonate decomposes to give lead 2 oxide and carbon dioxide. How many grams of lead 2 oxide will be produced by the decomposition of 2.5 grams of lead 2 carbonate? So here I didn't give you the chemical equation, you need to write it. So we're given the decomposition of lead 2 carbonate. So if lead has a positive 2 charge, I know that carbonate has a minus 2 charge, so that's already balanced. And it's going to decompose into lead 2 oxide. Lead has a minus 2 charge, lead has a plus 2 charge here. Oxygen has a minus 2 charge, so that's balanced. And we get carbon dioxide gas. These are both solids here. So looking at this here, the chemical equation comes already balanced, which is nice. So we want to know how many grams of lead 2 oxide will be produced by the decomposition of 2.5 grams of lead 2 carbonate. So if I have 2.5 grams of PbCO3, I know that 1 mole of PbCO3 weighs 267.2 grams. And I know that for every 1 mole of PbCO3, I need 1 mole of lead 2 oxide. It's a 1-to-1 ratio. And for every 1 mole of lead 2 oxide, I need to know the molar mass of lead 2 oxide, and that's going to be 223.2 grams. So the grams cancel, the moles cancel, and we're left with grams. And we get 2.09 grams. And that is our answer, D. Number 5 says, how many liters of NH3 at standard conditions STP will react with 5.3 grams of oxygen to form nitrogen dioxide and water? So we have 5.3 grams of oxygen gas. Now, important to note here that it's oxygen gas, so it's diatomic. So that means it's not 16 grams per mole, but it's 32 grams per mole. And we see here per every 7 moles of oxygen gas, we're looking for NH3, so we need 4 moles of NH3. And here we need to use that molar volume conversion, which says that for every 1 mole of any substance, but that includes NH3, we have 22.4 liters. So the grams cancel, the moles cancel, and we're left with liters. So we get, let's see here, do it on my calculator. We get 2.12 liters. So the answer here would be B. Number 6 is a conceptual problem. Which of the following is not a true statement concerning limiting and excess reagents? So let's work through each of these. The amount of product obtained is determined by the limiting reactant or reagent. That is true. A balanced equation is necessary to determine which reagent is the limiting reagent. That is true. Some of the excess reagent is left over after the reaction is complete. That is true. The reactant that has the smallest given mass is the limiting reactant. That is definitely not true. So that's going to be our answer here, D. But let's just look at letter E. Adding more of the limiting reagent to the reaction chamber will cause more product to be produced, and that is true. So the reactant that has the smallest given mass is not necessarily the limiting reactant. It could be, definitely could be, but it definitely could not. So you cannot make that as a rule of thumb. So that's why D here would be incorrect. Number 7 here says that propane reacts with oxygen in the air to produce carbon dioxide and water. We also can call that a combustion reaction. In a particular experiment, 38 grams of carbon dioxide are produced from the reaction of 22.05 grams of propane with excess oxygen. So that means that our propane is going to be our limiting reactant. So what is the percent yield of this reaction? So to determine the percent yield, we need to see what's the theoretical yield of carbon dioxide from the amount of propane that we're given. So we're going to convert the grams of propane into grams of carbon dioxide and use our percent yield formula. So we have 22.05 grams of propane. We know that 1 mole of propane weighs 44 grams. And for 1 mole of propane, we need 3 moles of carbon dioxide. Now, how do I know 3 moles of carbon dioxide? Well, let's think about this. If we're combusting propane, we're going to add oxygen gas, and we're going to get water and carbon dioxide as a product. So if I was to balance this reaction, what I would need to do is find the coefficients here to give me the same amount of elements on each side. So to do that, I would put a 4 in front of the water, a 3 in front of the carbon dioxide, and a 5 in front of the oxygen. I just happen to have dealt with the combustion of propane a lot before, so I happen to remember that. But you would need to write this formula out in order to remember this 3 moles of carbon dioxide. Now, once we get the 3 moles of carbon dioxide, we know 1 mole of carbon dioxide weighs 44 grams. So we get the theoretical yield as 66.15 grams. So this is our theoretical yield. I'm going to put this as theoretical yield. The percent yield is what we're looking for, and that equals actual yield, meaning what we actually made in the lab, actual yield, over what we theoretically can make. So your actual yield should never be more than your theoretical yield, and that's times 100. So what we actually made was 38 grams. What we should have made in perfect conditions is what we calculated, 66.15 grams. And we're going to times that by 100 to get the percent. And we get 57.6%. So the answer here would be B. So I just want to point out here, it got a little messy in the end, that in order to recognize the mole ratio here, you would need to balance the combustion of propane. Like I said, I just knew off of the top of my head that this was the coefficient of carbon dioxide in the balanced combustion, but you wouldn't know that, so you would need to write and balance the combustion yourself. Number 8 says that calcium oxide reacts with water in a combination reaction to produce calcium hydroxide. A 4.5 gram sample of calcium oxide is reacted with 4.34 grams of water. How many grams of water remain after the completion of reaction? So this was the question that most people got wrong. Not exactly sure why. I'm definitely going to go over it now, but not sure why. So if I'm saying how many grams of water remain after the reaction, I'm basically telling you already that calcium oxide is your limiting reactant and water is your excess reactant. So it saves you a little bit of time. By saving you that little bit of time, we can just use the mole ratio to find the moles that I make of each compound to find the excess water. And since it's a 1-to-1 ratio here, that's going to be easy. So I have 4.5 grams of calcium oxide. So I'm going to divide the grams by the molar mass of calcium oxide to find the moles of calcium oxide. So the molar mass of calcium oxide is 56. So that gives me 0.08 moles. That's an 8 there. And I have 4.34 grams of water. And we know water has a molar mass of 18 grams per mole. That's also an 18. So I get 0.241 moles. So like I predicted and knew, calcium oxide is the limiting reactant. So to find how much water remains, I'm going to subtract 0.241, and I'm going to subtract 0.08 from that to give me, let's see here, 0.161 moles, this is in moles, of water. And it wants the grams of water, so I would just say 1 mole of water is 18 grams. So I would cancel out the moles, we're left with grams, and we would get 2.9 grams of water. So the answer here would be C. So this problem shouldn't have been that bad. I think there was just some confusion. Hopefully this clears it up. You find your limiting reactant, you subtract it from the excess reagent, you convert the leftover excess reagent from moles into grams, and that gives you how much leftover you have. Number 9 says that a 3.82 gram sample of magnesium nitride is reacted with 7.73 grams of water. The actual yield of magnesium oxide is 3.6 grams. What is the percent yield of the reaction? So we need to find the limiting reactant, and then we'll take that limiting reactant and convert it into grams of magnesium oxide, and then we can use that in our theoretical yield calculation for the percent yield. So the easiest way to do this is to just convert each of these values into grams of magnesium oxide. So rather than converting them into moles and then rather than converting them into moles and then grams of magnesium oxide, we can just do that from the start, and it saves us that step. So to start off, I'm going to take my 3.82 grams of magnesium nitride, and I know that 1 mole of magnesium nitride from your periodic table weighs about 100 grams. And for every 1 mole of magnesium nitride, I need 3 moles of magnesium oxide, and 1 mole of magnesium oxide weighs 40 grams. So here I get a value of 4.54 grams of magnesium oxide. It's a little messy there, my apologies. Now I'm going to take my 7.73 grams of water and do the same thing. 7.73 grams of water, 1 mole, 18 grams. 3 moles of water, 3 moles of magnesium oxide. So I can already tell you that based on that the ratio here is 3-to-1 and this is 3-to-3, we're going to find that magnesium nitride is going to be the limiting reactant because we're going to get a bigger number here. But I will continue with the math. And we know that 1 mole of magnesium oxide is 40 grams. So when you type this in on your calculator, you get 17.1, like I said. of magnesium oxide. So we see that the limiting reactant is magnesium nitride. That should be an N. Nitride is the limiting reactant. So the maximum amount of product, or the theoretical yield of magnesium oxide, is 4.54 grams. So percent yield equals the actual yield over the theoretical. So the actual yield was 3.60 grams. We just calculated the theoretical, which is 4.54 grams. We times that by 100 to get the percent, and we get 79%, or to be more precise, 78.7%. So to save us a step, I went straight to grams of magnesium oxide. You could leave it at moles of magnesium oxide. That's still going to tell you the limiting reactant, but you're then going to need to convert it into grams in order to calculate the percent yield, since the actual yield was given to you in grams. And our last question here, let me just zoom in here so we can get a better look here. The last question says, how many grams of nitric acid, HNO3, can be prepared from the reaction of 138 grams of NO2 with 54 grams of water? So this is a simple limiting reactant problem. I'm going to convert my grams of NO2 into grams of nitric acid, and grams of water into grams of nitric acid. So here it asks for the grams of nitric acid, so I can't stop at moles here. It's not an option. I must go fully to grams. So I'll start with the NO2. I have the 138 grams of NO2. I know that 1 mole of NO2, let's see, well, 14 grams for nitrogen, 16 grams per oxygen, so that should be 46 grams. Just having a little bit of a mental blank for a second. 3 moles of nitrogen dioxide from the balanced chemical equation per 2 moles of nitric acid. And you can tell that it's an acid by the presence of hydrogen, but we'll talk about that at a later time. And 1 mole of nitric acid would just be 46 plus an extra 16 and 1, so it would be 63 grams. So that's going to give us 126 grams of nitric acid. So we do see that as an option here, but we need to make sure that the 54 grams of water doesn't give us anything less, because that means that would be the limiting reactant. So we need to be safe. And so 54 grams of water, 1 mole is 18 grams. We have 1 mole of water per 2 moles of nitric acid, and 1 mole of nitric acid is 63 grams. So when we type this in, we get 328 grams of nitric acid. So indeed, the answer here is 126 grams of nitric acid, meaning NO2 is our limiting reactant. So the answer here is C.